We will talk about random forest in this video. So we have already shown in decision tree that it's a high variance model. That means it overfits the data so much that it's not good in predicting for new incoming samples that what class they should belong. So to kind of address that problem, random forest or this kind of technique was proposed. It's a supervised learning algorithm that works on the concept of bagging. Okay, bagging, the word comes from bootstrap aggregating. I'll talk about it, what bootstrap means, what aggregating means. It's basically an ensemble method. It's a combination of outcome of many different models, and then a majority vote or a mean or median is taken to predict the final outcome of many models. It's very similar to, let's say, you want to buy a Tesla, and then you are trying to talk with many friends who have Tesla, and you are trying to maximize the number of friends. Okay, let's say if you have 10 friends having Tesla, you talk with all 10. If you have 50 friends with Tesla, you talk with 50. And then you are trying to ask them what are the pros and cons. Okay, and then you somebody says, okay, you buy, yes, you go ahead and buy. Somebody said, no, please don't buy it. And then 20 people says yes, and maybe 5 people says no among your 25 friends, and based on that you take the majority vote. So exactly that way random forest or this bagging algorithms work. Bagging means bootstrap aggregating. So bagging reduces the variance. Okay, that's the good part of it. So all these high variance models like decision tree it kind of gets normalized over many models and many predictions, and then the variance is reduced. So but bagging is not as effective for linear models because they typically have low variance and high bias. Okay, so it does not really make much difference for linear models. So you will find this question whether bagging is useful for linear models also. It's not that useful, but for high variance model by like decision tree it is. So bagging is useful because it works on the weak law of large numbers. Okay, weak law. What is a weak law of large numbers? Let's say we want to calculate the height of all the men in America. Let's say there are 100 million men in America. Okay, so and we want to calculate the mean of that. The mean height of them, but this entire 100 million men is our population, but the population changes frequently, like people born and the people die, so they are so you cannot sample all of them. So we sample a small set, let's say 100 people around us, randomly sampled identically and distributed, and you kind of calculate the mean from their height. So this is our this is our sample. So the population mean and the sample mean will be different. But it says that weak law of large numbers says that if you have a very significantly large sample size, then the probability of the difference between the population mean and the sample mean will be very, very small. That means the sample mean will come close to the population mean if you have enough number of samples. So this is called a weak law of large numbers. Okay, so if you have, basically it means that if you have large number of decision tree models and you combine their outcomes, then you can kind of iron out the variance and you have a good model, and that is the random forest model. So how bagging works, that is the important thing. So that it's in 3 steps. Okay, the first, you sample m data sets. We call them bootstrap data sets. Okay, bootstrap data sets. I'll talk about it, how to form that data set, and sample m data sets d1, d2 until dm from your given data set, which is D. Let's say you have a big data set D, and earlier on which you are doing the decision tree. Now you divide it in many small data sets and you call them bootstrap data set. And you how you create the data set? You create them with replacement. That means let's say you have n number of samples, you pick any random m from there where m is less than n, and then you create a data set. Okay, in any order. Order is also not important. So you can even choose multiple rows so that for any future choice you can also have that previous row which you already have selected. That's why we sample a row again we return that. Okay, we sample it, make a copy, and then return it. So the main population does not change. So we sample, the sampled unit is returned to the population before the next unit is drawn. Okay, so this ensures that the probability of selecting any particular sample remains the same in the future draw. So that's why this thing is very important, that you replace that sample which you have already considered. So that's why there is a chance of duplication of rows, and that's perfectly normal. Okay, so now for each this sample or bootstrap dataset DI, you train a classifier. That can be same classifier, it can be different classifier for different bootstrap dataset. Okay, and then finally what you do, you take a average or mean or median of the prediction made by that dataset. Okay, made by that model. So now if you take a very large M, that means your this number of bootstrap dataset is very large, then it's a better ensemble. But after some time, if it's a too large, then you kind of start losing the accuracy or the goodness given by that large M. So it's a point of diminishing return. Okay, so but if you have also, if it's a too large, then the classifier will slow down, right? Because you have to calculate decision tree for so many different bootstrap data sets. So, but it will not, the error will not increase. That's an important thing. So now for random forest, you see this. So let's say this is your data set. You have some positive samples, some negative samples, then some more negative samples, then some positive samples. What you do, you create multiple bootstrap data set from here. Let's say D1, D2 until Dn, n number of data sets. Okay, and they will have some samples. Okay, so there are two types of sampling possible. One is, as I already said, row sampling. You take the row and it's with replacement. Okay, consider that row, again return it, and then it's called row sampling, so that there is a duplication possible. Also there is column sampling. Okay, like you only consider a few columns, like we had that for decision tree. We had a age and alcoholic or not, and weight and BMI, all this kind of features were there. You may not consider all the features. Let's say among 5 features you only consider 2, and all the rows. So this is called row sampling. You can take with replacement, column sampling, or feature sampling with replacement, or both at the same time, both row and column sampling. So you can understand that D1, D2, Dn, all of them in size will be smaller than D. Okay, it will be smaller than D. So what is the possibility? An average 63.2% of the original rows will be in any of those bootstrap data set. Okay, it can be calculated using this mathematical formula, limit n tends to infinity 1 minus 1 over n to the power n, which is Euler's constant e to the power minus 1. It gives like 36.8% possibility that one particular row will not be selected in a bootstrap data set. So the remaining 63.2% is the chance that it will be selected. So all these individual bootstrap data sets are smaller in size than the main data set D, and then on each of them we train a model, okay, on this individual data set. So the DT1, our model for random forest, the classifier, the model is decision tree. Each of them will be trained using a decision tree, and then each decision tree will be will have a decision, and then we do a majority voting on that to do the final decision. It's very much like you ask your friend about the Tesla model and they give their decision, and based on that you take a majority vote and go for your decision. Now you see this majority voting is for classification problems, okay, like where yes, no answer, categorical outcome is there. But if you have a continuous variable as an outcome, then you take the mean or median of the and make it a regression. So you see, so this one shows that the mean of the outcomes. Okay, so for mean of the outcome, we take when the outcome is a continuous variable, and we take a majority vote when the outcome is a categorical variable. Okay, so this is overall the random forest, where we divide the data set into multiple smaller data set. We call it bootstrap data set, and then finally we aggregate the decision into one. That's why I call it a bootstrap aggregating, or bagging. There are many other bagging algorithms, and we'll talk about them.